And again, let me emphasize that we're assuming that sigma is a finite set. The set of classical states of this system X is not infinitely large, like the set of all natural numbers. It's finite. And that's just an assumption that we're making. For example, it could be that X is a bit, in which case the classical state set is the set containing two elements, 0 and 1. Sometimes we refer to this set as the binary alphabet. Another example is that X is an ordinary six-sided die, in which case the classical states are the numbers 1 through 6. Of course, we're talking about an abstraction here. An actual six-sided die may have many different attributes, such as its precise position, its orientation, its temperature, and so on. But with respect to the information that's most typically relevant when we're talking about a six-sided die, the classical states are the numbers 1 through 6, indicated by the number of dots on whichever side of the die is facing up. If X is a switch on a standard sort of electric fan that you might have in your home, then perhaps the classical states are the settings high, medium, low, and off. These are just examples. We could imagine systems having different classical state sets than these, but hopefully they convey the idea that this notion of a classical state is something that should be familiar and can be understood in simple and intuitive terms. Mathematically speaking, the set of classical states is just a finite set. And of course, this set must also be non-empty as well. There has to be at least one classical state that the system can be in, and there has to be at least two classical states if the system is going to be useful at all for storing information. Now, in some situations, we might know that X is in some particular state, but in many situations that arise in the setting of information processing, there may be uncertainty about the classical state of a system at a particular moment, so that each possible classical state has some probability associated with it. For example, if X is a bit, then perhaps it's the case that X is in the classical state 0 with probability 3/4, and it's in the state 1 with probability 1/4. We're going to refer to this as a probabilistic state, and we could express this probabilistic state as you see right here, simply by indicating what the probabilities are for the different classical states.
तो बेसिकली प्रोबेबिलिस्टिक स्टेट क्या हो गया कि एक क्लासिकल स्टेट में होने होने की प्रोबेबिलिटी बताता हुआ फॉर इंडिकेटिंग प्रोबेबिलिस्टिक स्टेट.
A more succinct way to express this probabilistic state is by a vector. Specifically, the representation that you see right here is a column vector, and this vector indicates what the probabilities are for the two possible classical states. To be more specific, the first entry indicates what the probability is for X to be in the state 0, and the second entry tells us what the probability is for the system to be in the state 1. This is simply the natural way to order the binary alphabet, or at least it's the way that we were trained to do this, with 0 first and 1 second. Going forward, we're going to use the term probability vector to indicate a vector like this. Specifically, it's a vector whose entries are all non-negative real numbers and where the sum of the entries is equal to 1. So it makes sense to think about these entries as being probabilities. Here in this example, there are just 2 entries because there's just 2 classical states of the system we're talking about. But in general, there could be any number of entries, with the understanding being that there's 1 entry for each classical state of whatever system we're talking about. We're going to continue discussing classical information, probability vectors, and so on in just a moment. But first, it's going to be really helpful to introduce some notation for describing vectors known as the Dirac notation. In fact, this is just the first part of the Dirac notation. There are a couple of other aspects of the Dirac notation that we'll see a little bit later in the lesson. This notation is going to be quite central to the way that we describe quantum information, so it's essential to understand how it works to do classical information. As before, we assume that we have a set sigma of classical states of some system. And let's assume that we have an ordering of these classical states, just like how we referred to an ordering of the binary alphabet in the previous example. Another way of saying this is that the elements of sigma are placed in correspondence with the integers from 1 to however many elements are contained in sigma, which is what this notation right here with 2 bars around sigma means. That's the number of elements in the set sigma. So there's a first state, a second state, and so on. The specific ordering or correspondence that we choose isn't actually going to matter all that much. What's really important is that we have an ordering and we stick to it. For many classical state sets that we'll encounter, there will be a standard ordering, just like we have with the binary alphabet. And if there isn't a standard ordering, we can just choose one. But whatever it is, the understanding is that we stick to it. Now, here's the notation that's being introduced. For any choice of a classical state A from our set sigma, we write this right here, which is read as ket A, to mean the column vector that has a 1 in the entry corresponding to A and a 0 for all other entries.
क्या हुआ? क्या जल गया? वो जला दो पंखा, एग्जॉस्ट। अच्छा, क्या हुआ लेकिन जला क्या? लाइट ऑन करिए। तेल भी जल सकता है? दैट्स प्रोबेबिलिटी है तेल की जलने की। सही है, ये तो पता ही था तेल भी जल सकता है। ये तो पता ही था तेल भी जल सकता है। ये तो पता ही नहीं था कि तेल भी जल सकता है। तेल जल सकता है, ये बड़ी प्रोबेबिलिटी कम थी इसकी, मतलब पता ही था मेरे को तो। नाउ दैट आई थिंक ऑफ इट। स्मोकिंग पॉइंट पे आ गए हम, साइंस ही पढ़ ली।
For example, if we return to the binary alphabet, which, as you might have guessed, is a very important example that we'll return to again and again, then cat0 and cat1 are the vectors that are defined right here. Cat0 is the vector that has a 1 in the entry corresponding to the classical state 0, which is the first entry, and a 0 for all other entries, and in this case there's only one other entry. Similarly, cat1 is this vector right here, where we have a 1 in the entry corresponding to 1, which is the second entry, and a 0 for all other entries, which again is just one entry. Here's another example. In this example, we have a classical state set sigma corresponding to the 4 suits in a standard deck of playing cards: clubs, diamonds, hearts, and spades. In this case, there really isn't a universally agreed upon ordering of these suits. For many card games, there is no suits in here. Clubs, cat diamonds, the general. We can do the same thing for any classical. Vectors of this form are called standard basis vectors. And it's a very basic fact about vectors that every vector can be expressed in a unique way as a linear combination of standard basis vectors. For instance, going back to the example from just a moment ago, the probability vector we saw can be expressed as you see right here. It's basically just an alternative way of expressing vectors that's going to be very handy for several reasons going forward. And with that notation now in our hands, let's return to the discussion of classical information and probabilistic states in particular. And let's consider what happens when we measure a system while it's in some probabilistic state. We might not ordinarily refer to a measurement or the act of measuring something in the classical setting, but the term makes sense. In essence, when we talk about measuring the system X in this context, we just mean that we look at it and we recognize whatever state it's in. Of course, when we look at the system, we don't Welcome to understanding C is the classical state A, which could be any state in our set sigma. This changes the probabilistic state of X in general, at least from our point of view. The probabilities no longer have any significance because we now know what the classical state of X is. It's A, and there's no longer any uncertainty about this. We see a classical state, and the particular classical state that we see is one that we can imagine is chosen randomly according to the probabilities. Now, you might object on philosophical grounds to the idea that the classical state we see is somehow chosen at random at the moment that we measure or we look at the system. The system simply was in some. We might not ordinarily refer to a measurement or the act of measuring something in the classical setting, but the term makes sense. In essence, when we talk about measuring the system X in this context, we just mean that we look at it and we recognize whatever state it's in. Of course, when we look at the system, we don't see a probabilistic state. We see a classical state. And the particular classical state that we see is one that we can imagine is chosen randomly according to the probabilities. Now, you might object on philosophical grounds to the idea that the classical state we see is somehow chosen at random at the moment that we measure or we look at the system. The system simply was in some particular classical state all along, and we just happen to have learned what the state was. But for the sake of thinking about the mathematical framework we're working with, it's okay to think about it this way, and doing so will allow us to draw a parallel with quantum information a little bit later. Let's suppose that the classical state that we see is the classical state A, which could be any state in our set sigma. This changes the probabilistic state of X in general, at least from our point of view. The probabilities no longer have any significance because we now know what the classical state of X is. It's A, and there's no longer any uncertainty about this. So we would now say this, that the probability that the system is in the state A is 1. We know this because we just looked at it and we saw that the classical state is A. So the new probabilistic state of X is one in which the probability of being in the classical state A is equal to 1. And that probabilistic state is represented by the probability vector ket A. We have a 1 in the entry corresponding to the classical state A and a 0 in all other entries. For example, if we again consider the situation where X is a bit and we have the same probabilistic state as before, then if we measure X, we can imagine that a transition takes place. With probability 3/4, we see the classical state 0, and by measuring, we transition to ket 0 being our probabilistic state. And with probability 1/4, we transition to ket 1. You can think about this as a transition of knowledge, if you prefer, as opposed to an actual physical transition. But what's important for the sake of this lesson is to recognize how the mathematics works. It's kind of trivial, actually, but by recognizing this triviality, the analogous description for the quantum setting might seem a little bit less mysterious. One final note is that to another person who didn't happen to see what the classical state of X was when we measured it, the probabilistic state naturally wouldn't change as a result of us having measured it. That's okay. Different individuals can have different knowledge of a particular system and correspondingly choose different probabilistic states to represent their knowledge of that system. In the last part of this discussion of classical information, we'll talk about classical operations that can be
Mm.
Performed on a system, starting with deterministic operations. When we perform an operation on a system, its state generally changes as a result. And in this context, the word deterministic means that the result of performing the operation depends entirely on whatever classical state the system was in prior to the operation being performed. In other words, there's no element of chance when a deterministic operation is performed. So there's no randomness or uncertainty involved. And correspondingly choose different probabilistic states to represent their knowledge of that system. In the last part of this discussion of classical information, we'll talk about classical operations that can be performed on a system, starting with deterministic operations. When we perform an operation on a system, its state generally changes as a result. And in this context, the word deterministic means that the result of performing the operation depends entirely on whatever classical state the system was in prior to the operation being performed. In other words, there's no element of chance when a deterministic operation is performed. formed, so there's no randomness or uncertainty involved. In mathematical terms, deterministic operations are described by functions. Every function f of the form that you see right here, which means that both the input and the output of the function correspond to elements of our classical state set sigma, describes a deterministic operation. The classical state A is transformed into the state f of A for each choice of a state A. For every function f of this form, there will always be a unique matrix m satisfying this condition that you see right here. And that is that by multiplying m to the vector ket A gives us the vector ket f of A. And that's true for every choice of a classical state A. It's not too hard to write the vector here. Elements of our classical state set sigma describes a deterministic operation. The classical state A is transformed into the state f of A for each choice of a state A. For every function f of this form, there will always be a unique matrix M satisfying this condition that you see right here. And that is that by multiplying M to the vector ket A gives us the vector ket f of A. And that's true for every choice of a classical state A. It's not too hard to write down an explicit description of M given whatever function f of this form we've chosen. It will always have exactly 1, 1 in each column with every other entry equal to 0. And here's the formula. The BA entry of M is equal to 1 if B is equal to f of A, and otherwise it's equal to 0. And by this we mean this is the entry of M whose row corresponds to B and whose column corresponds to A. We'll see a few examples in just a moment, and we'll see why this formula works. Now, it might not be clear why we would want to take a function and express it as a matrix like this, but it does make sense to do this. One of the reasons, and perhaps it's the main reason, is that if we have a system in a probabilistic state and we perform a deterministic operation on that system, then the resulting probabilistic state can be obtained by matrix vector multiplication. That is, if our system is in a probabilistic state that's represented by some probability vector v, and we perform the deterministic operation described by m on that system, then the resulting probabilistic state will be given by m times v. Here, by the way, this arrow with a little bar on it like this is just a common notation in mathematics for indicating how one thing gets mapped to or transformed into another thing. You could just use an ordinary arrow, but this is conventional and it's recognizable.
4 थैली।
And maybe it's a little bit more specific than just an arrow, which could mean many different things. Now let's take a look at an example, or a collection of examples, really. Let's consider what happens when we take our classical state set sigma to be once again the binary alphabet. There aren't too many different functions of the form we've been discussing when this is our classical state set, and to be more precise, there are just 4 functions of this form. Here those 4 functions are described by their so-called tables of values. The first table describes the first function, which we've named f1. For each possible input on the left, we list the corresponding output on the right. So f1 of 0 is equal to 0, and f1 of 1 is again equal to 0. And that is to say that f1 is the constant 0 function. It always takes the value 0. The second function, f2, is the identity function. The output is always equal to the input, as you can see from the second table. The third function, f3, is described by the third table. f3 of 0 is equal to 1, and f3 of 1 is equal to 0. This function is better known as the not function, or logic.
एक सेकंड 60 रुपए नहीं 40 रुपए पाओ तो 40 रुपए 40 रुपए पाओ
Logical negation. We sometimes also call it a bit flip because it flips 0 to 1 and 1 to 0. The last function, f4, is again a constant function just like the first one, but this one is the constant 1 function because it always takes the value 1. And those are the only 4 functions from the binary alphabet to itself. Here are the 4 matrices that correspond to these 4 functions. They're described by the formula from before, which you can see right right here. And if you're so inclined, you can pause the video and check this. Just remember that with matrices, the order of the indices is always rows first, columns second. So the BA entry corresponds to row B and column A, or the row that corresponds to the class classical state B and the column that corresponds to the classical state A. So, for example, if we look at the first function, we have that f1 of 0 is equal to 0, and correspondingly, the 0, 0 entry of m1 is equal to 1, while the 1, 0 entry, which is right here, is equal to 0. And you can do the same thing for the case where the input is equal to 1, and similarly for the other three functions. You can also check that this formula from before is true, and you can just go one by one through all the different possibilities to verify this. And in fact, if If you think about the way that matrix multiplication works, really you can just kind of eyeball this. When you multiply a matrix to a standard basis vector like this, you can imagine that you're taking the input and dropping it into the top of one of the matrices, in whichever column corresponds to the classical state inside of the ket. And the output that you get is simply that column as a probability vector. So, for example, M3 multiplied to ket 0 gives you 0, 1 as a probability vector, which is ket 1. M3 multiplied to ket 1 gives you 1, 0, which is ket 0.
आना लगा दो, एक काम करो। हाँ, ब्रेक।